and welcome to the lecture today. And I will first to share my screen. So I hope you can see my screen already. So I'll have my laser point. So yes, I think we can slowly start now. I think maybe some students will join a little bit later. And as I mentioned last time, so today we will have an introduction of the stimuli-responsive polymers and their properties. So as a first point, of course, so we should know what are the stimuli-responsive polymers. And so as you know, so when the polymeric gels or networks, when they can, so under some special environmental stimuli response, they will show a kind of volume transition or phase separation. So then it's called a kind of stimuli responsive polymer. So this means, so when we change the local environment, so here the local environment means either temperature, pH, salt concentration. In some special cases, of course, we can also change the field, like electric field or magnetic field, or you can even change the pressure. Then you will see a kind of volume transition or phase separation in the system. So this is called a kind of stimuli responsive system. And so in this case, so the polymer chains, they will have transition from the swollen state. So in swollen state, the interaction between the polymer chain and the solvent, these are the dominant interaction. So this is at the swollen state. So they will transfer from the swollen state to the collapse state. And in the collapse state, so the interchain, so polymer chain interaction, they will be the dominant interaction. And in this case, so from this plot, it will be more easy to understand. So it means, so when we change the temperature or salt concentration or pH, so the volume or the stiffness of the polymer hydrogel, so they will change. So either so at a special like temperature region or concentration region, you have like a phase transition. So it can be either so from the swollen state to the collapse state, or opposite, or from the collapse state to the swollen state. And then in this case, these are two different phase transition behaviors. So when it's run from the swollen state to the collapse state, like the red line here, then it calls the LCST behavior. And if it's like the opposite, the blue line here, then it will be called UCST behavior. So it's like a low temperature, and another is up temperature. So these are like two major different phase transition behavior. So I just give you one example. So how the polymer chains will, the interaction, will change if we change from, so in this case, the stimuli, the temperature will be the temperature. So it means when we have temperature lower than the phase transition temperature, the 31 degrees Celsius, then the polymer, so this is polynepon, so it's polyisopropylene acrylamide. So it is at swollen state at lower temperature, and it means the polymer chains, they will have interaction with the solvent. So the solvent is water, so they will have the hydrogen bonding with water. So this is the main interaction in the system. Then when we have the temperature, so we increase the temperature above the transition temperature, LCST, yeah, the transition temperature, then they will transfer to the collapse state of the polymer chains. And in this case, the interpolymer chain, so the polymer-polymer interaction will be the dominant because the hydrogen bonding at high temperature will be broken. And meanwhile, so you can also see at lower temperature, because they have hydrogen bond with water, so the polymer chains are more hydrophilic in this case. But when we increase the temperature, the hydrogen bond will be broken. And then in this case, the polymer chains will be more hydrophobic. So you have on one side this volume change when we change the temperature. And on the other side, you have the hydrophobicity change when we change the temperature. And this is the main transformation of the polymer system when we change the temperature as a system. And later, so in the second part of our lecture today, so I will show you so how we can use such kind of transition, yeah, for different applications. So here you can see from the photo, because on the left side, so this is at lower temperature, so the polymers, they are hydrophilic, so they are swallowing in water. You see it's transparent, but when we increase the temperature, the polymer became hydrophobic, so it became collapsed and not so soluble in water. Then you see it become turbid here in the solution. And if we have like different form of the poly chains, of course, you will also have a different state of such kind of phase transition. Here are three different examples. For the first example, if we have a kind of single polymer chains, then under this phase transition temperature, so when the temperature is smaller, so lower than the LCST, so they are at a swollen state, you have a coil, yeah, of these polymer chains. And when we are at higher temperature, so higher than this phase transition temperature, then the polymer chain will also collapse, then you have a kind of groove polymer chain state. And on the other side, of course, you can also have a kind of networks, the polymer networks in a macroscopic state. So normally it's called macrotubules. So it means in a kind of bulk, yeah, macroscopic networks. And in that case, so when the temperature is lower, then it's a kind of hydrophilic microtubule at swollen state. And of course, when you increase the temperature, then the networks start to shrink, collapsed. Then you have a kind of hydrophobic polymer networks, and it's in a shrunk state. And similar, so, but here, if you can have a kind of network in a form of microgel, so it means it's in a size in the around 100 nanometer to micrometer range, so it's called a microgel. And in that case, so when you have the phase transition temperature, so when the temperature is lower than the phase transition temperature, we have a swollen particle, so it's at a swollen state, hydrophilic swollen particle. When you increase the temperature, then you have a kind of shrinkage of this particle. And meanwhile, you have also the particle will become more hydrophobic. And this can be also, of course, yeah, used for different applications due to this kind of transition. So as I showed this also last time, yeah, when we discussed about the different methods for the synthesis. So the typical, yeah, methods for synthesize such kind of microgel is called precipitation polymerization. So I just want to remember you again, yeah. So here is the typical, yeah, so the napalm monomer. So this is the base. You have two double bonds, so this is the cross linker. And then of course you can add additional functional groups. So here you can have like also to sort concentration sensitive or pH sensitive, yeah. If you have an OH group here, so then it's pH sensitive system. And using SDS as a surfactant, it can be also synthesized without SDS. And so APS is ammonium potassium sulfate. So this is the initiator. And so you can have the polymerization at 70 degrees Celsius at high temperature. Yeah. So, and for around 4 hours, so you will have a kind of very good monodispersed microgel system after the polymerization. And so here is a kind of polymerization mechanism. So in the beginning, we will have a kind of oligomer radical. So you have a radical, yeah, on the oligomer. Then, yeah, when the growth of the particle will form a kind of particle precursors, then it will like have more and more polymer chain, yeah, on the particle. You have a growing of your primary particle, and then finally at the end stage, you will have a kind of cross-linked microgel particle. In this case, of course, you have like several parameters, yeah, to control such kind of polymerization process. So for example, you can control the cross-linker amount. So then you can, of course, control the cross-link density. And by control the cross-link density, you can, of course, control the porosity of the particle and also the content of solvent here, which can be encapsulated in your microgeos or network system. And of course, you can also very well control the size of these microgel particles depending on the surfactant, so amount of surfactant you will use, and also the initiator concentration. And in that case, so for the microgel, normally you have the size like from 100 or 50 nanometer to a few micrometers. And if the size are even smaller, then you can call it's not microgel, but nanogels. So in the case of nanogel, so you have the size around a few, like 10 to 30 or 40 nanometers, and it's called nanogel. So it's also the same, yeah. So it's a cross-linked polymer networks. And of course, yeah, so they will have a kind of responsibility to different stimulus, and they will show the phase transition, yeah, or foreign phase transition. Here, so you can see the typical morphology of such kind of microgel system. So on the left side, so the upper left side, so this is a transmission electron microscopy. And so this is at a dry state, I should say. Later, I will also show you the electron microscopy, which is done at a quiet state. So then you can see the totally different morphology. But so here you can see, so this is at dry state, say homogeneously monodispersed particle. And so from the scanning electron microscopy, you can even see a very nice morphology of this particle. And maybe you will also realize, so it's different from these polystyrene spheres. Yeah, you see the particle actually they are like lying because they are soft. Most of the particles they contain water, and after drying, because this electron microscopy they have been done under dry conditions, then of course the water will be evaporated. Then this soft particle, of course, they will lying, yeah, like attached on the substrate. So you see, so they are not like a hard sphere. Yeah? You see very nice like a spherical particle. So in this case, it's like very nice. Yeah, so attached on. In some cases, you even difficult to take this SEM image because they will make a kind of film. Yeah, saying you should do atomic AFM, yeah, to distinguish the morphology of this microgel system. And here, a very convenient methods to determine the size of this microgel is dynamic light scattering, so DLS. So I also mentioned once in the beginning of our lecture, by using dynamic dielectric scattering measurement, you will get the hydrodynamic radius or hydrodynamic diameter of your particle. And of course, by this method, you can measure your microjoule particle as a function of temperature in this case. Then you can see typical the behavior. So at lower temperature, the particles are at a swollen state, so they are larger size. And when you increase the temperature, the particles they start to shrink at their collapse state, and you see the decrease of the particle size clearly by the dynamic light scattering by DLS measurement. So, and also here, the authors have also to investigate the amount of additional functional monomer in the system, and they can see with the increase of BA in the system, so you see the decrease of the particle size. And so this is like a kind of homogeneous microjoule particle. Of course, you can also design a kind of causal microjoule system. In this case, so I show you also one example. So you can use polystyrene particle as a core. Then you do this seed mediated, so emulsion polymerization. So you use polystyrene particle as a seed here. Then you also run the emulsion polymerization, and then the cross-linked polynipon, they will deposit it onto the polystyrene seed surface. Then you will get a kind of causal microjoules. And so you can see, so this is AFM image here. You see they are very nice monodispersed. And of course, AFM is also, so in this case, it's performed on the dried condition. And as I mentioned, so at dry condition, actually you cannot distinguish this shell clearly from the polystyrene core, because at drying state, your polymer networks, they will shrink here and collapse. And one very good method is using the cryo-electron microscopy. And actually, so I think in up to a few weeks, so in June, we will have a special topic on the cryo-electron microscopy. So it's a very promising method, because you will, for the sample preparation stage, you will shock flows of your sample under liquid nitrogen or liquid ethane. In that case, so the water, so the liquid water will be transferred into the glassy water, and to avoid the formation of ice. So this is a critical point for the cryo-electron microscopy. And then in that case, you can investigate the morphology of your particle in their native state as they disperse in water, because in that case, because the water has been transferred into the glassy water, then from the electron microscope, you will not see it. And so from this image here, you can see clearly, so the dark spherical particles, this is polystyrene core, then you will have a corona around this polystyrene core. So this is the cross-linked polynipon network. You can even do the cryo-electron microscopy, prepare the sample at different temperature. So this is like the prepared at room temperature. You see the thick polynipon network here as a shell. You can, of course, prepare your sample to increase the temperature, then polynipon's network is shrinkage. Then you see, so when you prepare the sample at high temperature, you see the decrease of the thickness of polynipon. So this is also a very good improvement of this temperature sensitivity by electron microscopy. And so such kind of causal particles, they are quite, give quite a lot of advantage if you want to study their behavior or want to apply them for some special catalytic application or other applications. For example, so in this case, so you can very good control the particle size by the cross-link density. And also they they are colloidal stable, so they show excellent stability. And of course, yeah, you have the polynipon network as a shell. Then you will have under the different temperature, they show the reversible, yeah, swelling and diswelling, yeah, behavior. And also for the polynipon, they have a special complexation with the metal ion. So such kind of particle will be a very good nanoreactor if you want to, for the immobilization or embedding of the metal nanoparticle. And this we'll also discuss in the later part of our lecture today for their possible application. And here I just want to mention, then of course, yeah, so as I mentioned here, for the polystyrene particle by emulsion polymerization, you can choose different surfactant. Then of course, we can also change the charge, yeah, of your particle surface. It can be either positive charge, yeah, or negative charge. And then in this case, yeah, so you can of course measure the surface charge of your particle by theta potential measurement. And this you can also measure as a function of temperature. You will see, so these solid dots here, so these are the core particles, so polystyrene. And you can see, you can measure the theta potential, yeah, of your polystyrene core. You see they are more or less constant when you measure at different temperature, because for the polystyrene core, nothing changes, yeah, if you change temperature. But in the case of the microgel particle, you see they also show a kind of transition, yeah, when you change the temperature of the solution. And so you see, so this is for the negative charge microgel. So at lower temperature, they are swollen, and the surface charge, yeah, actually they are smaller. And when you increase the temperature, when the particles are totally collapsed, you see the increase of the surface charge. And similar behavior you can also see from the positive charged microgel. This is because for the theta potential, you measure, of course, the average surface charge on your particle surface. And when the microgel is swollen, so you have a big volume, because the number of the charge on your particle surface, this is constant. So when you have a high volume or high surface, yeah, the average number of the charge on the surface is lower. So that's why you have a lower theta potential number at a lower temperature. But when you increase the temperature, then your particle start to shrink, yeah. So you have a smaller particle, so you have smaller surface, yeah. In that case, meanwhile, it means because the total number of your charge is the same, but when you have decrease of the surface, then it means you have the increase, yeah, of the surface charge. And that's why you see the increase of the theta potential. And this is also quite logical, yeah. So you can even follow this LCST behavior by the theta potential measurement as a function of temperature. And another thing you can use is, instead of this free radical polymerization using commercial KPS, yeah, as the initiator, you can also run by the photopolymerization. This is because I want to show here. If you look into detail of this cryo-electron microscopy here, you see. So actually this polynipon shell, they are not homogeneously deposited onto the polystyrene core. You see quite a lot of holes on the surface. This is because there's actually no special control on the polystyrene surface. This is like a free radical polymerization, and then the polynipon chains, they are like radically deposited onto your polystyrene surface. And if you want to improve the system, of course, it will be nice. You can control the polymerization of nipon directly on the polystyrene core surface. And in that case, so you can modify your polystyrene particle so with a thin layer photo initiator. So it means so you can, using at the last stage of your polymerization, you add the photo initiator, you also have double bond here. So that's why it will covalently graft it onto your polystyrene core particle surface. And then as a next step, So you use a UV light as a light source. And under this UV light irradiation, so the photoinitiator will be decomposed and will generate the radical on the polystyrene particle surface. Then of course it's radicals, yeah, so that's why you have a like surface, yeah, initiated polymerization. So you have, in this case, very controlled, yeah, the growth of your polynipon chain directly on the polystyrene core surface. And here, so you can also see very nicely of the morphology of such kind of calcium microgeles by cryo-electron microscopy. And you can see clearly, yeah, so in this case, the polynipon network, they do, yeah, homogeneously grafted onto the polystyrene core surfaces. And you do not see such kind of loops, yeah, on the surface. So it means, so by photoimmersion polymerization, you can well control the deposition of the polynipon onto the seed particles. And you can even, yeah, do the photoimmersion polymerization with different amount of, so this is a cross-linker for polynipon. And in this case, so when you increase the amount of polynipon cross-linker, you can also decrease the size of your microgel. So you see the decrease, yeah, of the thickness of the polynipon shell. So this is also a very well and controlled method, yeah, to prepare such kind of microgel system. So here I just want to let you have a direct comparison, yeah. So this is by the conventional immersion polymerization, you see a lot of loops, yeah, on the polystyrene surface. But by the photoimmersion polymerization, you can well control and have a homogeneous deposition. So of course, yeah, you can also have some even fancy structure, yeah, and to play around with such kind of polymerization methods. So here I just want to give you one example from the group of Japan. So this is a group of Suzuki. And so his group did quite a different way for such kind of polymerization. You see, they use microgel as a seed. So they first prepare a kind of microgel, so it's a negative charge microgel. Then they use styrene as a monomer, yeah. So oppositely as we did, yeah. So they use this as a seed and also do the seeded emulsion polymerization using styrene as a monomer. And so they also, yeah, try to investigate the morphology of their product, yeah, by cryo-electron microscopy. So you can see, so the polystyrene particle, yeah, they are formed. So they can really use such kind of soft network as a seed. So you see like separated, yeah, polystyrene particle can be generated in such kind of microgel system. And you can see, so they, of course, yeah, also trying to investigate. So this is a SEM image. So this is like under the dried condition. So you dry the sample, and again, you see, so the particle are lying on the substrate. But this is also very well to investigate, yeah, the morphology. So you have a kind of red band structure. So you have this polystyrene particle embedded into these soft networks. And they also try to understand the mechanism. So why they will form such kind of complex morphology. And so in this case, they feel, so the styrene, of course, they will like to, because styrene is kind of hydrophobic system. And when they have like inside like more hydrophilic and the shell around is like hydrophobic at high temperature, that's why the polystyrene particle will prefer to immobilize into this hydrophobic layer. And there you will have a kind of first nucleation, yeah, of the polystyrene, and then the styrene monomer will, of course, yeah, then swollen your primary polystyrene particles and then glow there and to form like the final polystyrene particles. Another system, so you can, of course, to give more functionality to your microgel system. So here I give you one example. So you can, so this is typical, so temperature sensitive polynipon. And of course, you can incorporate this photothermal active nanoparticle into your microgel. Then in that case, you will have a kind of photothermal responsive system. Then instead of using temperature, you just use light as a source. So photothermal responsive particle means, so if you will shine light, so under light irradiation, they will generate heat. So you do not need to heat your system anymore. You just use the light as a source. Then the particle will transfer this light into heat, and then so when they will work as like a heater for your microgel system, then of course the local temperature will increase. Then to lead such kind of phase transition of the microgel particles. So this is one example. So this group, they are pioneer. In this case, they use polydopamine, one of the most high efficient photothermal material as we know now. So they use polydopamine and as a light source, so as a photothermal particle, and to embed it into the microgel system. And you can see, so of course, on the different concentration of the particle, so when you switch on the laser light, here they use 808 nanometer laser as a light source, and under the constant intensity, and also for a constant time, so you will see, so the different, they will generate like, so the solution temperature will change there, so increase like depending on the concentration. So from 10 to in the highest concentrations, they can even so increase the temperature to more than 30 degrees Celsius. So then this difference of the temperature, of course, is enough to lead to the phase transition of the microgel system. So then we also use this concept to design our microgel particles. So we use a polydopamine particle as a photothermal source, so photothermal nanoparticle. And for the polydopamine here, one difficulty we have met here is so it's difficult to use this directly as a seed for the seed emulsion polymerization for the polynipon, because the polydopamine, they have too many chemical functional group on the surface, and it's impossible for you to do the surface polymerization directly. What we have done is, so we have covered the polydopamine particle with a layer of silica, and then with silica, of course, then you can modify the silica surface very easily, and you can find this MPS precursor of silica. You will see, so here you have double bond. With this functional silica precursor, you will have a kind of double bond modified silica layer. And then you can do, of course, this seeded emulsion polymerization, use this particle as a seed. And then the polynipon network will be generated onto the polydopamine particle surface. And you can see from the quiet-electron microscopy here, so the dark color polystyrene particle, and then you have the light corona, so this is polynipon shell. And of course, so you can follow the synthesis procedure for each step. And this is normal, so the classical TM after dry state. So you see, this is very nice monodispersed polydopamine. and you coat it with a layer of silica. And then, yeah, after that, you will have a layer of polynipon coated. And here you can also have a direct compare. Yeah, so this is at dry state electron microscopy, and this is cryo electron microscopy. So you see very nice. Yeah, so for the joint TM image, so the polynipon, they shrinked. Yeah, so you see only a very thin layer of this. But in the case of cryo-TM, because they are in swollen state, so you see a much larger particle, yeah, in that case. And of course, yeah, you can try to investigate their photothermal behavior. And so in this case, so we're trying to see the photothermal effect, yeah, of these particles. So on one side, of course, you change the concentration of your particles, and you can see, so when you change the concentration, so you can have the increase of the temperature of the system. So from like you have room temperature as a starting point, at the highest concentration, you can increase the system, yeah, to more than 45 degrees Celsius. And if you look at, yeah, so you can also redraw this in this scope. So you can see, so you can increase the temperature for more than 25 degrees Celsius by simply change the concentration of the particle. Yeah. And then in this case, you can really convert the light into the heat. Another microgel system, actually, I also introduced you last time. Yeah, so instead of polynipon, another well-studied system is polyvinyl caprolactam. And this microgel particles, they also have LCST behavior. So lower temperature, they are swollen state. High temperature, they start to shrink. And so the LCST, so the transition temperature for the polyvinyl caprolactam is a little bit lower than nipon. So for the polynipon, it's around 32 degrees Celsius. And for the polyvinyl caprolactam, you have around 28 degrees Celsius. And so you see, you can, of course, yeah, also choose another functional monomer. Then in this case, you do not need additional surfactant because here you have more hydrophilic system, yeah? And use this as a cross-linker. And normally you can use those, in this case, we use this AMPAN. So this is azo-based initiator. And in the end, you will have a kind of cross-linked microgel particle. And here, you, of course, you can very good, yeah, as I showed you already in our last lecture. So you can well control the particle size of this microgel, and they show very good stability, colloidal stability of due to the polyvinyl caprolactam. They also have photothermal, also they also have the temperature sensitive swelling, diswelling transition behavior. And another advantage here I also mentioned last time, so for the polyvinyl caprolactam, they are biocompatible. So that's why they are now very well studied system for different kind of bio application, like drug delivery and for such kind of application. So this is a typical, yeah, SEM, so electron microscopy, scanning electron microscopy image, and this is the AFM image, yeah, of the particle. You see they are also quite homogeneously and like a spherical structure. And you can also follow the transition temperature of such kind of microgel by dynamic light scattering measurement. And you see, so they have a transition temperature around 28 degrees Celsius. And also here, so here is, you can, of course, yeah, change the functional monomer concentration. So here's AAEM concentration here in the microgel system. And of course, with the increase of AAEM, you will have a smaller particle size in that case. So it's like you can really well define your particles, yeah, by the different parameter during the synthesis. what you can do more on such kind of microgel system is, so you can functionalize your polyvinyl caprolactam. So here, so using this cyclodextrin, so CD molecules. And CD molecules is so they have such kind of structure, so like a special hole. And so this kind of structure, because we see they are well defined with the size here. So this is the size of this well-defined structure. So it means they have a special complexation ability with different molecules. So only for molecules smaller than their size, they can have a complexation and go into this. And this can be, of course, also be applied for some special applications. And also for the polyvinyl caprolactam particle, it can be also used as a nanoreactor for the generation of gold nanoparticle in the system. So this is also a very good nanoreactor for the metal nanoparticle deposition. So here, so they have tried to incorporate different amount of this alpha CD into the polyvinyl caprolactam microgels. And so in maximum amount, they can put in 13% of this alpha CD molecules grafted into the microgel system. And of course, so this can be well studied by the FTIR spectroscopy. And they also study the change of the particle size as function of temperature by dynamic rate scattering. So in that case, so you can see, so this is more clear to see. So after the incorporation of alpha CD into the microgel, they still preserve this LCST behavior. So they still have like at lower temperature, they are swollen, then at high temperature, you have the collapse of the system. So here I just give you an overview, and instead of this, so I introduce mainly two different microgel systems. And of course, there are different kind of monomer can be used and to synthesize such kind of functional, so temperature sensitive polymers. So you can see, so you can have a different functional group onto your chains. And in that case, of course, so each individual system, they will have different transition temperature. So this is really system dependent or the functional group dependent. Really depend on the application. So you can always look into this table and try to find the appropriate system you would like to work with. And actually, so until now, most of the work has been done based on this isopropylamide, so NIPON system. And this is because this is really one of the most model system and the classical system. But it does not mean so other systems are not good, just because so since a lot of work has been done on this system, so that's why it's well studied. And people would like to use this model system and to investigate their different applications. Another point I want to also discuss with you is, so you can give additional functionality into your microgel system. And in this case, so for example, you can also generate temperature or also pH responsive system. And so this is our typical, so if you want to have a pH sensitive microgels, so you can have different monomer to choose. So either anionic comonomer or cationic monomer. So for the anionic comonomer, so this is mainly based on this acrylic acid or malic acid. So you see that's all, you need an acid group here. And in that case, so normally, so when you increase the pH, you will have a swollen state of the. system of the microgel or the networks. And when you decrease the pH, you will have a collapse state of the microgel. And in the case of cationic copolymer system, it's different. So here you have the imidazole, and in this case, so when you increase the pH, actually you will have a collapse system. And when you decrease the pH at acid state, then you will have a swollen and positive charge network. So this is just keep in mind, yeah. So for the pH responsive system, really depend on what kind of comonomer you have. And I just give you one example, what we can do, yeah. So with such kind of both temperature as well as like ions or pH sensitive material. So in this group, they also use nipon, and then the comonomer they use imidazole, phenylimidazole. And what is interesting, so here they're using this bromide with Accutane. So this is their cross-linker. This is because you have here, so you will have counter ion, yeah. So this is due to this ion interaction. So that's why, so when you have this as a cross-linker, so you have this bromide with Accutane here. So this is actually can be broken if you have additional salt inside. Then you, of course, yeah, you will broke such kind of ion interaction. And this is the group they used, yeah. So that's why this is ionic microgels. So they add additional salt inside and to block these cross-link chains and to release these small dye molecules. So this is methylene orange, yeah, from the system, which is negative charged. And you can see clearly, so after you add salt inside, yeah, so its color will be totally changed. This is because you release all the dye molecules and it will be moved away. Of course, so you can generate a kind of polymer actuator. So based on such kind of concept. And so I hope you also, I think you have seen this already, because you can even buy such kind of plant here from the supermarket. Actually, I also bought last year, yeah, also one. So this is called this, I checked them later because actually I know such kind of plant, yeah, but I'm not sure what is the right name for it. That's why I checked, yeah, from the internet. Then I found, so this is called Venus flytrap. And I do see, yeah, so they have a kind of a stimuli on the leaf, yeah. So when you touch this small needle on the leaf, then they will close immediately. And this is called a kind of actuator. And for the polymer system, they can work similarly. And so normally when we talk about the polymer actuator, so they are polymaterial, then they can change size or shape here when you have a kind of variation in the environmental conditions. And this is like, say, based on such kind of mechanical work. And of course, you can also do the similar using like temperature, thermal responsive polymer actuators. And so in this case, so of course they are environmental friendly because you use only temperature as a stimuli response things. And they can be, depending on the polymer system, you will choose. So they will also be possible bio compatible. Then they can be used for the bio application. And of course, they can be very easy design and synthesize. And for the thermal responsive hydrogel, so here, so one thing we should keep in mind, so you need water. So when it's dried, of course, they do not show such kind of responsibility because they need like water as a solvent. And then you see the imbue or expel of water from the microgel system. Or then of course, yeah, so you can design your system, and using bi-layer polymer, you get a kind of actuator. And this actually is what I want to introduce, yeah, for you as an example, how you can do such kind of bi-layer, yeah, as an actuator. So on the left side, so this will be a kind of macrogel or hydrogel, yeah, it's homogeneous. So you have a bulk here, gel. So when you increase the temperature or decrease temperature or change pH or other system, yeah, so you can have a non-swollen like collapsed state or to the swollen state, yeah. So this is like homogeneous. So you see a kind of exchange of the photon transition in a homogeneous way. Of course, you can change the system. So either you change the field, yeah, then you will have a kind of inhomogeneous deformation. So then they can bend, or you can use bilayer system to induce a kind of inhomogeneous hydrogel. For example, like one will shrink, the other will swollen. You know, you have so many different systems you can choose. Yeah? Then, of course, then if you change the temperature pH in a homogeneous field, they will still, because they lead to a kind of inhomogeneous layer phase transition, then they also can get a kind of bend mechanical, yeah, this deformation. And this is what the actuator would like to have. Yeah? And this is group from IPF, so from Inov. So he's now a professor at University of Bayreuth. So he is also one of the pioneer working on such kind of polymer hydrogel based actuator. You see they can even form a very beautiful you can actually design your system in different form, like a flower made or like a stem or stars, or other shape, and depending on, so you can have like one layer is like swollen and the other is like shrink. And when you change the temperature or pH of the system, then you can always have like open, so either open or they will close under different kind of stimulus. So this can be used as an actuator. Then another very important application I want to talk with you is such kind of microgel. So they can be used as very nice nanoreactor for the immobilization of different inorganic nanoparticles. So you can either like, depending on what kind of nanoparticle, or filler you want to embed it in. So you can either have like controlled conductivity or controlled catalytic activity in the case of metal nanoparticle, or if you have iron oxide, you can even have the magnetic response of your microgel system. And because you have the microgel, so you have either the biocompatibility of your microgel. So normally you can have a temperature or pH sensitive system. And they are normally, for the microgel, they are colloidal stable. So you can combine the both advantage into a one composite system. This is the thermal responsive or stimuli-responsive polymer system. So this so give a very nice overview. You can see, so it can have different form like core shell structure, or like a kind of yolk shell particle, or you have a core and then the brushes, or even have like microsphere, or the networks, or kind of accumulate or aggregates. So you have really different kind of polymer network based on these stimuli-responsive polymers, which can be used as a nanoreactor for different metal or metal oxide functional nanoparticles. And then, of course, you can use this temperature or stimuli responsibility. Yeah? So here's one example. So they use gold nanoparticle because gold particles are plasmonic. They have a very strong plasmonic effect. Yeah. Then they embedded this gold nanoparticle into a kind of ordered array structure and embedded into the hydrogel system. Then when you change either pH or the light, yeah, then the hydrogel will start to either swollen or shrink. And in this case, then you will of course change the distance, yeah, of your plasmonic nanoparticles. And this of course will change the surface plasmonic absorption effect of your particle. And you see from the photo, you see you will change the color of your substrate when you change like pH or temperature in that case. Another, of course, beauty of this system. So here's one example. You can combine most often, so like gold nanoparticles is the most well-studied system because gold nanoparticle here is like you can have either gold nanorods or spherical gold nanoparticle or even like star-like structures, yeah, embedded with this polynipon. Say the combination will bring you a kind of new synergies of your complex system, especially for the optical application in this case. And so I just want to give you, so Professor Kumacheva, so from Canada, she is one of the most, so first one, yeah, in the world working on this system. So you can see, so actually her group did this already 15 years ago. And they are really the first one, yeah, working on it. So they use the microgel particle, modify the acrylic acid, and then you have like the pH, yeah, sensitive microgels. And they use this as a template for the deposition of different nanoparticles like semiconductor particle or metal nanoparticle or even magnetic particle. And they show really the first one, so use this as a carrier system. And so here they have also measured, so due to the stimuli-responsove, yeah, of your microgel template, then they can change. So here they use for the silver. So you see they can even change the optical property. Yeah? So this is fluorescence sensitive, yeah, silver nanocrystals, and easily, yeah, by changing the pH of this microgel system. Then you see they change of their photo properties. And so in my group, actually, we also did quite a lot of work in this direction. So you know already the system, so this caution microgel, yeah? Then you can immobilize the metal nanoparticle into your polynipon network in 2 steps. So in first step, you deposit this metal precursor, so normally it's salt here, so you dissolve in water, then you add, then the metal ion will be absorbed into the networks. Then in the second step, using sodium borohydride as a reducing agent, then this absorbed metal ion will be reduced into the responsive metal nanoparticles. And this can be well studied, yeah, by quiet electron microscopy. So in this case, it's silver nanoparticles. They can be well deposited into these caution microgels. And depending on the network, so when you have a high cross-link network, you will see you will have smaller, yeah, so the silver nanoparticle can be generated, they are smaller if you have a like dense cross-linked microgel particle. So this is even possible, yeah? And of course, so you can also deposit different kind of metal nanoparticle instead of silver. So in this case, we use like gold, platinum, rhodium, or even bimetallic nanoparticles. So in all cases, you can see you have a very nice, yeah, homogeneous system. And these metal nanoparticles, these are small black dots here. These are the metal nanoparticles. They are well deposited into these caution microgels. and you do not see any nanoparticle in the solution. Yeah? So this is also a kind of proof. So microgel particle can be used as very good carrier system or template system, yeah, for the deposition of metal nanoparticles. And so this is like the thermosensitive behavior of the microgel template. And you can also measure after the deposition of the metal nanoparticle. And here you compare these two plots, and you can draw a conclusion. So in this case here, so you do not see any difference. Yeah. So this means after deposition of the nanoparticle, you still have this temperature responsibility of the microgel networks. And of course, yeah, so you can also investigate your some responsibility by cryo-electron microscopy. And here we use this for the catalytic application of the embedded nanoparticle. If you imagine, so this is at lower temperature, so polynippon network, they are swollen. And in this case, so there should be no limitation of the diffusion of the reactant into your networks to react with the nanoparticle embedded inside. And when you increase the temperature, then your network start to shrink. And it means it's similar like your system is kind of closed, yeah? And you will have a kind of diffusion barrier, a high diffusion barrier for your reactant to diffuse into the network and to react with the nanoparticle. And in this case, actually, you can play around with temperature, the catalytic activity of the nanoparticles. And so in that case, we use reduction of nitrophenol as a model reaction. So this is for nitrophenol. It can be reduced into the 4-aminophenol using sodium borohydride as a reducing agent, and the metal nanoparticle embedded in the microgel as a catalyst. And the reaction is a very good model reaction because you see from photo already. So for nitrophenol have nice yellow color, and aminophenol is colorless. So you can follow the reaction by UV spectroscopy under the reaction time, so as function of reaction time. And so the absorption of the nitrophenol at 400 degrees Celsius. So you just follow the absorption intensity of the substance. Then you can do the quantitative analysis of your catalytic reaction as a function temperature. So you can get the rate constant of your reaction very precisely in this case. And so of course you can measure the rate constant of the reaction as function of temperature in this case. So you see we draw it in an Higgs plot way. So it's 1 over absolute temperature. And for these green points here, so these are for the normal Plato nanoparticle, which are embedded in a kind of non-thermosensitive polymer templates. And here you see a typical linear behavior of this Higgs plot. And so here for this part here, you see the totally different way. Yeah? So for the red point, so this is a Plato nanoparticle embedded in the microgel. For the blue point here, these are the silver nanoparticles embedded in these temperature sensitive microgels. And we can see, so at lower temperature region, so this part, they still follow the linear behavior. This is because at lower temperature, the network, they are swollen, yeah? So there's no diffusion limitation, so they still follow this Higgs plot behavior. And when we increase the temperature further, you see, so in this case, the network start to shrink. Then you see the decrease of the rate constant. So the reaction slow down until the particle is totally collapsed. So here it's a transiting temperature. So it means, so the phase transition of the networks, they do play a very strong role on the catalytic behavior of the nanoparticle. So when the particle is totally collapsed, And in this case, when you increase the temperature, so then this photothermal effect then is dominate again, yeah. Then you see the increase of the reaction reactivity again. So this is one of the first improvement, yeah, on this using the photothermal behavior of the network, yeah, to tune the catalytic activity of the nanoparticles. And so, of course, the microgel can be also used as a nanoreactor if you want to control the deposited metal. In this case, we're trying to use it as a reactor for the in situ growth of the gold nanorods into the microgel particle. And for this system, so you can use the gold nanoparticles, the spherical particle, which are pre-generated in the microgel as a gold seed. Then you do the seed-mediated growth step for the gold nanorods. And from the QuickTime image here, you can see clearly, so the gold nanorods here, they are well defined and deposited into the microgel system. And the gold nanoparticle, very interesting is their optical behavior. So this is why people are working on it. So because they can show two different surface plasma absorption band. So one at lower wavelengths, so this is responsive to the transversal surface plasma absorption band. And you have another absorption band at the longer wavelengths. So this is corresponding to the longitudinal surface plasma absorption band. And interestingly, so when you measure this UV spectroscopy as a function of temperature, you will see there's a obvious red shift of this longitudinal surface plasma absorption band. So when we measure, so from the room temperature, so you have the absorption at around 800 nanometer. And when we increase temperature to 34 degrees Celsius, you see you have more than 30 nanometer shift of this band. This is, you can even, so you see very nice shift. And you can also join the shift of this surface plasma band as a function. So this is the blue point here as a function of the particle size of the microgel. You can feel very well, so fit with each other very well. And this is because, so when you increase the temperature, the polynippon network, they start to shrink here. On one side, so you will change the refractory-redox index of your polymer medium on your gold nanorod surroundings. And this is actually the main reason so why you can using the volume transition to change the optical properties of your nanoparticle. And as a chemist, of course, you can always do one step further to have even more fancy system. So in this case, so you can use the gold nanorods as a seed and then to deposit the secondary metal nanoparticle into the system. So here you see the platinum nanoparticle can be deposited onto the two tips of the gold nanorods. And this can be well defined here. You see clearly from the cryo-electron microscopy here. So the platinum nanoparticle can be well defined, deposited onto the two tips of the gold nanorods. And of course, so it's always nice, to show an overview instead of single nanoparticle, to show the system, do works. So you can see nicely, so the nanoparticle system. And the deposition of platinum can be also confirmed by the EDX mapping of the images here, and you see the peak of platinum on it. And meanwhile, of course, you can also follow the optical property of your particle. So you see after deposition of platinum on the two tips, you have red shift, because in that case, you have a kind of elongation of your particle because the length aspect ratio of your gold nanorods are increasing. That's why you have a redshift. And on the other side, you have a broader and decrease of the absorption intensity. Yeah? And this is because, of course, platinum is not plasmon, do not have this plasmon effect. Yeah? So that's why when you have additional platinum, you actually will eliminate the surface plasma property of the gold nanorods. So you see like the decreasing of the absorption intensity and the broad of the peak. So this can be also used, so such kind of particle can be also used as a catalyst here for the reduction of nitrophenol. And here, so this is the rate constant of this reaction measured as a function. So we use the surface area of the nanoparticle in the system for the comparison. And this actually related, so the surface area also related to like the concentration of the particle, yeah. But the surface area, because the particle surface is the catalytic active part. So this is more precisely if you want to compare the catalytic activity of each of these particles. And here I just want to mention, so the blue points here are the platinum deposited gold platinum nanorods. And they show the highest catalytic activity. So that means after deposition of platinum, you will enhance the catalytic activity of your gold nanorods in the system. And of course, they also show the nonlinear behavior as usual. This is due to this volume transition of the network. So it means even for such complex system, you can still tune the catalytic activity by the volume transition of the microgel. Instead of this metal nanoparticle, so you can also, of course, deposit other systems. So here I give you one example. So you can also generate the titanium dioxide nanoparticle into the microgels. And here, one very important, so you should control the water amount for the hydrolysis of the titanium dioxide, because if you have too many water, then you lose the control of the reactions and you do not have a homogeneous titanium dioxide deposited on the surface. You will have a kind of bulk titanium dioxide, big pieces in your system. And you can see here, so these are the high resolution TM of the titanium dioxide. So you see, so they have a well-defined lattice bridges. So these are corresponding to the anatase phase of this titanium dioxide. And we also measure the cryo X-ray, so transmission X-ray microscopy. So this has been done by the synchrotron based on BASI2. So the X-ray microscopy, the advantage here, so instead of make a image or the morphology, you can study by the X-ray microscopy. Most important is so you can even make the spectroscopy. So you can measure the next subset spectroscopy of your nanoparticle. And so this next spectroscopy can help you to confirm what kind of crystal phase you have for the titanium dioxide. In that case, you see we have, so this orange measured from the, so this black, so this is a reference sample we mixed together with our particles. Yeah? And you see, so this anatase reference, so the peak are well fit. They show similar with our hybrid nanoparticles. So this also confirms the formation of anatase nanoparticle in the microgel templates. So then later, when we think about the catalytic application, so of course it's even better if you can have an isolated gold nanoparticle surrounded by polynipon networks. And then in that case, so we can start with a gold silica causal particle, then coat it with the silica with MPS, as I mentioned. So MPS will bring the double bond onto the surface. Then you can do the surface parameterization of polynipon network onto it. This can be also confirmed, yeah. So from the TM image, so you can have like gold core, silica metal shell, yeah, and the polynipon network on the surface. And then as the last stage, so the silicon nanoparticles, so the silica shell, yeah, can be etched by the sodium hydroxide, so under base conditions. And then you will get a kind of yolk shell particle. And in that case, yeah, of course, all the reactants will be controlled by the diffusion into these polymer networks. And this will be a nice system, yeah, if you want to study the catalytic activity as function of temperature for the microgels. And here, so we use two different reactions. One is, again, the reduction of nitrophenol. Another system is the reduction of nitrobenzene. So you compare these two molecules, you see actually nitrobenzene has a similar structure, but you do not have OH group here. So this molecule is more hydrophobic compared to the nitrophenol. And interestingly, so we measure the both reaction as function of temperature, as you can see from the plot here, yeah. So blue points are for the reduction of nitrophenol, red points are the reduction of nitrobenzene. First of all, you see, yeah, so in both cases, you do not have this linear behavior, so it means the foreign transition, yeah, so they will turn the catalytic activity, which is like similar like we have found for other thermosensitive microgel system. What is quite interesting for us is, so at lower temperature, so at this region, you see the reaction of nitrophenol is much faster than that of nitrobenzene. And when we increase the temperature, and you see they totally different. This means, so at lower temperature, the polynipons, they are swallowing water, so they are more hydrophilic. So in that case, hydrophilic molecules, yeah, so the nitrophenol reduction is more favorable. And when we increase the temperature, the polynipon networks, they start to shrink. Then the system is more hydrophobic. And in that case, the reduction of nitrobenzene is more favorable because this molecule is more hydrophobic. And it means you can control, yeah, the catalytic activity, yeah, not only by the porosity of the network, but also the hydrophobicity of the microgel system. And then in that case, you can not only tune the catalytic activity of your reduction, but also the selectivity of the different molecules there for this reduction reaction. Another step you can do, of course, so you can even use this gold nanoparticle as a seed, yes, and you do again this seed mediated growth. And then depending on the gold precursor, yeah, you add here, so you can increase the core particle. Yeah, so originally it's around 30 degree, around 30 nanometer, I think. So you can increase to 60 nanometer and even to 100 nanometer. And depending on the concentration of the gold precursor, then of course you can also follow the UV spectroscopy of the surface plasma absorption band of the gold. Yeah, you see obviously, yeah, red shift, and this means the growth of your nanoparticles. Instead of this gold or metal nanoparticle, you can also invent the metal oxides. So I give you one example on the cube oxide nanoparticles. And so cube oxide is a very nice system. So it's a kind of p-type semiconductor, and they have been quite widely applied in different applications like lithium-ion batteries, gas sensors, or as a photocatalyst. And the advantage for the cube oxide is, so they are very easy to synthesize, and also they are very cheap material. But the disadvantage or the big challenge if you want to do the surface modification of this nanoparticle is, you know, the copper oxide is, you have the copper 1+. So it's very easy to be oxidized to the copper oxide, yeah, to 2+. And also they are sensitive to pH. So copper oxide is very easily to be etched if you change the pH condition of your reaction solutions. And so for us, actually, we worked or struggled quite a long time, yeah, to do the surface modification of the copper oxide nanocubes. So we can synthesize, so using SDS as a factant. So we can synthesize copper oxide nanocubes. And then we have developed a kind of surface modification methods. So we mix the PDDA. So PDDA is a kind of cationic polyelectrolyte. So they have the positive charge. And we mix this polyelectrolyte with sodium styrene sulfonate. So sodium sulfonate, so you have a double bond. And in this case, so you can bring the double bond onto your copper oxide particle surface. And with this double bond, then we can do the surface polymerization with polynipalm. And to get, so this is after the surface modification, you will have a well-defined particle here deposited. And after the surface polymerization, you will have deposited the polynipalm network onto your copper oxide nanocubes and to have a kind of causal nanoparticles. And so this you can also follow, yeah, by the dynamic light scattering. So these causal particles, they are temperature sensitive. And what is also very nice, we can show, so we can measure the quire electron microscopy on the different temperature. And so the size of this nanoparticle, what we can obtain from the quire electron microscopy, they fit well actually, yeah, to what we can determine from the dynamic light scattering. So this means, so we do, yeah, see the phase transition of this causal particle when we change the temperature. Another advantage of the coating of the polynipalm is, as I mentioned, so the copper oxide particles are very easily to be oxidized. So you see, we measure, so on the left side, these XRD patterns. The red curve, so the black curve is the original, yeah, copper oxide after synthesis. And after storing for 10 days, you see, so we have additional peak appeared on the XRD pattern. So this peak corresponding to the copper oxide. So it means, so the copper oxide has been already oxidized after 10 days of stoning. But for the polynipalm coated particle, we have done the similar measurement, and we also take the XRD pattern after storing for 10 days. And here you see nothing changed. So you can improve the stability of the copper oxide. And also after coating polynipalm, the colloidal stability has been also enhanced. You see, so after storing for overnight, they are still stable, but here you see they totally precipitate. So in this case, so this is a really, by polynipalm modification, you can have a kind of very well-defined system. And of course, so as I mentioned, copper oxide has been used as a photocatalyst. So in this case, we're also trying to investigate the photocatalytic activity of this particle using the methylene orange, a kind of molecules or dimolecules. So you use the light. After irradiation, you see the color is gone, and you can follow this reduction, this degradation reaction by UVB spectroscopy. You follow the decrease of the absorption peak of the methylene orange, then you will get the rate constant of these photo degradation reactions. And so then we measure the two systems. The one is with Nippon shows this is the pure oxide. And you see, after the black points here, after coating of polynipon, you can enhance the photocatalytic activity of the system. And this we can also be confirmed. So we try to measure the absorption properties of the methylene orange of these two particles. And we can see here, so the red points are after Nippon coating. So first of all, so after the Nippon coating, we can enhance the absorption behavior of the polynipon causal particles. And the second thing we have measured is we're using this ESR spring trapping to determine the radicals that can be generated on the light irradiation. And we found after the Nippon coating, the causal particle, the radical, they can generate much more than that of the pure cupric oxide. This means so much more these hydroxide radicals have been generated by the causal nanoparticles. And these hydroxide radicals, they are the active species for this photodegradation reaction. That's why we have the enhanced photocatalytic activity after deposition of polynipon shell. Another so we can work on is gas sensor behavior. And interestingly, so we use this causal microgel, and by the cooperation of Professor Palzer, so he has moved to TU Dortmund since last year. And so they have developed a kind of inkjet printing method. So you can use the inkjet printing to deposit a layer on the gas sensor chips and then use it directly for the gas sensor test. And very interestingly is so for the inkjet printing, of course, we need a kind of proper concentration of viscosity of your solution. And we found is so if we use the pure cupric oxide nanoparticles, you need to have a concentration around 8% weight percent. Then it can be in a good printable range as inkjet printing. And after coating of the polynipon network, you need only 1.5% of the particle. So in this case, you see you need much less amount of the particle to get this printable behavior and to have a homogeneous layer of this gas protein. So you can see in this printable range. And also, so you see from the SEM images here, so with the causal particle after Nippon coating, you have a much homogeneous deposited substrate compared to that of like a pure cupric oxide nanoparticle. So here you see really a lot of aggregation, and this is inhomogeneously deposited on the substrate. And that's why, so when we use this to test the gas sensor behavior, so the Nippon coated systems, they show much better gas sensor sensitivity. So this is here, so red points here. So you see, so they show much higher sensitivity, so responsive to this resistance of the NO2 gas. And of course, another advantage here is because you need very less amount of particle, so the material cost will be much lower in that case. So this is really very promising, another promising possible application for the polynipon networks. And with this, I can come to the last slide of our lecture today. So I hope, so after the overview introduction of this stimuli-responsive system, you will have a general idea, so how it works and what kind of stimuli-responsive polymers there will exist, and also how you can use their stimuli responsibility to define different applications. And of course, yeah, so there will be still a lot of possibility you can do on such kind of system. And most important, of course, yeah, is to understand the behavior. So why they will have the phase separation, or why the thermodynamic behavior of such kind of polymer systems, and to use them into different applications. And they will be, of course, especially because you then have a kind of smart materials. And actually, last week, I just read one new article, so one paper published in Advanced Material. They also use a kind of hydrogel, so polynipam hydrogel, and embedded with this polydopamine. So as I mentioned, polydopamine is photothermal, yeah. And this is the work has been done in Princeton University from US. So they have a piece of hydrogel. It's black because polydopamine is black, yeah. And because polydopamine can absorb light, yeah. And then you can use it to the wastewater treatment. Then you use it like to absorb water at lower temperature. And when the light is shining on it, then it will hit your hydrogel. Yeah? Then the water will be expressed, yeah, from your hydrogel, and then you can get a kind of water self-cleaning system. So with this, I have gone through, yeah, all the content I want to show you today. So is there any questions from your side?
Yeah, I just have one question. Thank you so much for a very nice lecture. What is the piezo valve? The last slide you showed?
Sorry. Which slide do you want to?
Yeah, the piezo valve that you show the lower row and left.
This is for the, this is for this electric, how to say, so with a kind of like can switch on and off, like electro resistance, so you can control it. This is like the piezo wave, yeah. They have really different application.
Thank you so much.
No problem. So I do not hear there's any further questions. So then I wish you a nice weekend. And so then we will meet again on next Friday. And so on next Friday, we will talk about this porous polymer materials. So then, bye.